All right, great. So next up we have Jan Wafels, who will be presenting computer vision algorithms for our users.
Good afternoon. So my name is Jan Wafels. I'll be talking a bit on computer vision. I have a small company called BNOZAC here in Brussels. I'm probably the most, let's say, ecological one here attending it because I went by bike to the conference, just for your information. So we also provide support on R, automation, these things, and provide support for the R community. Have our own useR repository here, about the closest one probably from this center. So, and we give also a lot of training. So if you're interested in text mining, machine learning, applied spatial modeling, computer vision, also advanced training, R package creations, automations, and continuous integration, Shiny, big data, it's all provided by us. So if you go to the website, some of the trainings are given at the university also. So I'll talk a bit about computer vision in R. So apparently I'm the only one here talking about computer vision here at useR. So, but there exist already quite a lot of things in R. For example, you have Magic, a package which is good for data for manipulation images. ImageR is good for interpolation, warping, filtering. EB image is good for biological applications. OpenImageR, edge detection, manipulation. Then you have a lot of domain-specific processing for R packages. You have something called AD-Impro for smoothing, texture analysis, Fourier transforms, brain images, plankton analysis, wood identification, thermal images, image clustering, tumor detection, spatial point patterns. And you have also, R is good at interfacing, so you also have already quite some packages. It's a bit scattered all over the world, mostly on GitHub. You have something called R Vision and R OpenCV Lite. You have all kind of interfaces to Google and let's say to Microsoft API services. There exist also recent packages like Keras R and also TensorFlow, so you can do a lot already. So I'm just going to talk here about 5 or let's say 6 extra packages which were developed recently by us. And they were mainly developed because we needed it to, let's say, for a number of use cases, namely identifying products based on images and doing some quality control in some factories where they have electronic devices, and also for inputting for further processing. So for that, we developed 6 more packages, and they're all available online, so there's open source, and also this presentation can be found at our GitHub repository, so if the Wi-Fi would work, so you can go there. So there are 6 ones. One is called image corner detection, F9, canny edges, line segment detector, contour detector, dleap, and darknet. So I will just go over them all one by one, so they're available here at the GitHub repository, if that would work. Yeah. So, and some packages are also still under development. So I'll start with all these, going over them quite quickly. So the first one is image corner detection F9. So, and it's implementation of the Fast9 corner detection algorithm. So what does this do? It basically detect blobs in your images, and these blobs can then be used to track objects. That's basically what you're going to use it for. And the idea of this Fast9 is that if you have certain area in the image, and then you're looking around the image, and if the pixels in that, so near that pixel here are brighter or darker, depending on some kind of threshold, this is called a blob. That's the idea. And so I made a package for that, image corner detection F9, and it does this. And it's based on C code, so all the code here that we'll be using, it uses the RC++ package from Dirk. So that's, it's using C or either C++ code. So let me show you this, how this works. So if I have an image, let's say of chairs here, then you read in the image, you have to use as input a grayscale image, so it's just numbers between 0 and 255. And then you have a function called image detect corners, which is part of the image corner detection F9. And then you can plot the results. So let me show you this here. So here I have an image called chairs.pgm. That's just an image based, which I can plot right now. I'm using the readPNM package, function from the Pixmap package. And if I plot it, it will appear here. And then I can also use the function image detect corners. Okay, and if I have this here, I have a data frame with points which were detected. So basically it detects here points. So if it plots here, you'll see a red points detecting corners of the image. So that's one example here. Another package which is on there, it's called, it's for image canny edges. So it implements the classic edge detector called canny edges. So what does it basically do? It's a number of steps in order to find edges of certain area in the image. So it does first remove noise. It finds out the gradients. So basically the direction of, let's say, pixel intensities. It keeps only the maximum of these intensities, and then you have some kind of threshold. If it's above some kind of intensity, you keep the edge. And you remove, let's say, edges which are closer to other edges. That's basically it. So there's again, using RC++, a package called image canny edges that we implemented based on C code that you find here. So basically what you can do is, again, you get the same type of image, you read it in, for example, here with read PNM from the PixMap package, the same thing that I just showed. And then you have a function called image canny edge detector, and then you just give the result. And it gives you this nice, well, if there would be less people here, it will be it will be something different. So you get the edges of a certain area in the image. So that's another package. Okay, 8 minutes. I have another package called image line segment detector. So why is this useful? If you want to detect lines in your image. It's based on the line segment detector here. And what are the, let's say, how can you detect lines? They're basically zones in the image where the gray level is changing fast enough from dark to light. So if you would have a look here, you'll see that, yeah, so this is a line, this is a line, this is a line, this is a line. So that's basically what this algorithm does. It's a very recent algorithm, and it basically is going to look again for gradients, and these are the gradients here, and it's going to, let's say, subdivide these spaces of gradients where they go in the same direction. That's basically what it does here. So you see this gradient goes in that direction, this is in that direction, and then it builds rectangles around it. So that's the logic of this image of the line segment detector. It's based on C code, which is also which you'll find there. So if then let's go to the next slide to show that here. So suppose that I have an image here of a building. I can find the lines on of the building itself. So let's show this here. So I have here again this grayscale image. In R, if you read it in, it goes from 0 to 1, so it's grayscale, so values from 0 to 255. So I multiply it by 255, I have about 860 line segments. So if I would plot the image, and I can also now add the line segments to that image, so you'll see that happening. So now I know where the buildings are, and it's in R. So if all the 860 things will show up, the plotting, yep, it's there. Okay, you'll see it follows exactly the lines of the building, so that's fine. So that's one image show here. It was used to detect lines in houses. Another package, it's called image contour detector. So basically, and all these packages are in different packages because the C or C++ code was at different licenses. That was the reason. So this one allows you to detect contour lines. So it's based on this paper here. So again, what the logic of this is, it removes low frequencies of noise from the images, and basically it looks for contours of lines. So this could be a contour line, and it separates two adjacent regions. So this one here and this one, and it basically looks for uses an existing edge detector and finding lines, and these lines are approximated by a circular arc. That's the idea of this, and then it uses a test, a Mann-Whitman test, to see if these intensities are really different. So that's it. So again, it's based on C codes. If you want to use it here on R, it's pretty simple. You have the same setup. It's now the function is called image contour detector. So if you have here an pretty car, let's say, or you have an old style car here, a contour detector, I can give an image contour detector. It will find the contour lines 192 here, and if I would just plot these contour lines, it will show me, well, it's a Volkswagen, so you see here the contour lines of the of the car. So that's another one. 5 minutes. So if you go back. So if you have an image in another format than let's say a grayscale image with values from 0 to 255, you can easily use the magic package to read an image like a JPEG image and to convert it to another format. For that, the magic package is really good here. So here I have an image of the Atomium, so you'll go tonight at the Atomium, or maybe some of you guys. And then again, you can run the image line segment detector to find the lines in the image. So you see here at the text where the Atomium is. So again, the same side of setup. In this case was just a few more lines of code here to convert the JPEG image here to a PGM image. And then I can use the function image line segment detector here, and then it's going to find the lines in the image here at the Atomium. So that's fine. Keep it in mind if you're going to go tonight to the reception. Another thing which is relevant is identification of certain points. So this is a package called image dlib. It allows you to do two things here, namely to identify speed of robust features, so the SURF algorithm. So what does this do? It locates objects here, faces, and it's used to reconstruct 3D scenes and to track objects. So what is this? A SURF descriptor basically will identify, again, points in the image, and it will give you a 64-dimensional description for each point in the image. That's basically the idea behind it. If you're interested in the math, you can go there. And again, so it's being used here, for example, to detect if this here is a license plate or whatever kind of thing. So you have, let's say, a database of license plates, and you get a new image, and then you're going to match the SURF descriptor of your image with the database descriptor, or the SURF descriptors of all the images in your database. So that's the logic. Again here, how do you do that? Is a function called image SURF. In this case, it only works with BMP data, so with BMP images. So if you give image SURF here, so what this will return you is a list of points. So again, SURF blobs. So it has found points. In this case, it found 296 points here, and you have the image descriptor. So that's normally used. So you have, for each of the 296 points, you have a descriptor of these points. That's it. And that can be used traditionally in other machine learning models. So that's the idea. So if I would do this here on this nice boat here, so it will detect a bunch of points here, these lines, and also the sky here. And then you can use it with other packages like k-nearest neighbor to match the points with other points in a certain database. Another package, another part of this package is called the image dlib. It allows you to compute HOC features of an image. So it's mostly used to detect pedestrians in a certain image. So this image, basically the idea is you break down the image in a bunch of cells, and then again you get a certain vector which is describing the gradient structure in that cell. So that's the idea. So again, here you have a simple function in R, which is part of the image dlib package, which allows you to get you that descriptor. So if I would have a look here, so I have this thing on the boat here. So here I have, for each of the cells, I have now a 31-dimensional descriptor, and that can be used in other traditional machine learning models. So that's the idea. So that's this package, and the latest package is called Image Darknet. It's an interface to Darknet. So if you're interested in that, so it's a neural network library, a big deep learning library. So where you give in so-called YOLO, or you only look once. So what can you do with it? You basically have a function called image darknet detect, and that one will basically detect the locations of certain objects inside of your image. So here we're in Belgium, so this is an image from Madrid. So you see here a bird, a person, a chair, and a sports ball, because ici n'est pas un sports ball. It's from Margriet. Yeah, okay. So for the ones who are from Belgium. So how does this basically work? You're gonna define the darknet model here. Basically, the darknet model is a deep learning model, and then you can, with a certain number of weights, so you trained the model. I'm not going to go into detail on how to train this model, but you can go to the website, and then you can detect. So you can detect an image. So if I would go here, image is not there. You can detect the image here based on the model. So it's now going to load here the darknet model, so the convolutional neural network, and it's going to see which things are in there. And another thing that you can do here with this convolutional neural networks in the darknet here is to classify an image. So with this here, it says, well, it found here a cat and a person. Another thing is that, so it also detected the location of that, so this area. And another possibility is that you use image darknet classify, and then it's going to say, well, there's this dog on side of it. So that's basically what it is. And my time is up. So if you have further questions, you can ask me right now or ask me after the break.